You're not supposed to show this.
Alright. So hello, I'm Andrew Nakos, and this year I'm studying aerospace engineering at ISM. Just to tell you a little bit about myself, I play lacrosse and indoor soccer. Those are team pictures from our most recent seasons. Last year, the lacrosse one, that's from varsity last fall, and then indoor was last winter. We won the championship, actually. I think that's pretty cool. And then I have my family consists of my parents, my two brothers. One of them goes here to Frisco. He's a sophomore. The other one's in 8th grade at Hunt Middle School. And it sums me up pretty good. And then I chose aerospace engineering because it's been pushed on me a lot since I was a little kid, since that's what my dad wanted to do. But he unfortunately failed out of engineering at college, and so he switched to business and law, and because it was too hard for him. And then he's definitely pushed me along the path, and I actually really like it. A few years ago we took a trip down to Houston and visited Space Center there, and just seeing a rocket there that wasn't actually used. It was for the Apollo 19 mission that actually never occurred. So yeah, I thought that was really cool, and that kind of locked me in on the path, and I've stuck with it ever since. And then this is my quote: "Ships are safe in their harbor, but that's not what ships are for." That's by John A. Shedd. And I said, well, I need to get out of my comfort zone. I need to do something cool. So I took ISM, because if I stayed in my harbor, which would be my home or my comfort zone, then I wouldn't be fulfilling my purpose. Okay, and then this is the path to success. So a big thing that the counselors and teachers and administrators are pushing on us is going to college and getting good grades and planning out your future now before it's too late. So there are several skills that are key to aerospace engineering. So the first is problem solving, and I'm taking high-level math classes, physics, and other classes that help my problem solving and critical thinking skills that are so key and vital to aerospace engineering. Because without these skills, then you really have nowhere to go in the field. And then on to college. So these are 3 colleges I've been looking at for aerospace. They're all top 10 in the country, in their respective field, which is aerospace. Although they may seem, they're all public schools, because college is very expensive, if you didn't know, and I'm trying to save money while still planning out my future and giving myself the steps for success. Okay, so I'm moving on to the actual research now, and I'm going to start with the interview assessments. So for this first one, financial viability, it came from my first interview with Mr. Dustin Miles from Lockheed Martin. He's not an aerospace engineer, he's actually a materials engineer, and so a lot of the stuff he does is along with financial viability in his field. So he tries to cut costs on the labor for the F-35 Lightning, and so he talks a lot about the structure of the company, their assets and liabilities, and the importance of their financial success as a company, because that's his job and what he does. Okay, he said some key points from his presentation, or our interview, was that Lockheed Martin spends $1 billion a year in labor on about the F-35. They have over 10,000 employees, and if you include their subcontractors, they have over 15,000. And it's the F-35, one F-35 plane takes 2 years to produce. So it's a invested project, very invested project. And an interesting tidbit that he came up with was that around 2/3 of their labor costs are hiring people to try and cut the cost for the actual plane. Okay. And then from my other interviews, I really learned a lot about the design process that came from engineering. So there are 3 main phases. The first is the actual design phase, where people come up with a concept and then they like design it in a computer to something that's engineeringly feasible. And then the second phase is construction, where they actually build the plane or the helicopter, the drone or whatever they want to build. And then the third phase and final phase is testing, where they test to see if what they're making will work. So to go a little more in depth on the design phase, there are actually sub-phases to the design phase. So the first sub-phase is brainstorm, where they identify the problem and they come up with solutions to the problem in engineering teams. It's kind of, instead of more engineering, it's more of a visioneering thing at this phase because it's really preliminary. And then they move into design, where the employees make the concept into an engineeringly feasible project. So what they actually do is like they take their concept and they have to like plug in the equations and stuff to make sure that it'll actually work and be financially viable in the economic field. They do this this is an example of a brainstorm. Like they decide, oh, what would be the best way to get from point A to point B. So like they could say a helicopter, an airplane, or a drone. And that's like a little more in depth on the brainstorm. But then the part two of the design phase is where they actually, sketch out what they're going to make. They're going to like make blueprints. Like that's an example from the F-35 over at Lockheed Martin. And then once they do the drawing and the rough sketches, then they put it into a CAD program, which is like a design program. Like we've been learning about that since freshman year when, like, I don't know if anyone else took intro to engineering, but what we did mainly was practice like designing in these programs because these programs are the core of the engineering field. And so once they actually put it into the CAD program, they simulate tests to make sure their parts will work, like they connect with each other well, and they'll survive, like both financially and structurally. Then after it passes this phase, if the concept passes the simulated test, it moves into the construction phase. And one of the most key things in construction is efficiency, because they're trying to save money so that they make the maximum profit from their designs. So there are two main things that you see in construction. You have flow and ease of access. So flow is important in order to reduce travel time between places. For example, at Lockheed Martin, they have 4 like lanes in their production plant. One for the wings, one for the body, one for the tail. And so all of these start at the outside and they work on their way to the middle so that they can meet up and be put together for final assembly where the finished plane will exit the building. And if they had to increase the travel time between like each workstation, then it would cost a lot more money and it would just not be as good. Okay, the second most important thing in construction is the ease of access. The employees need to effectively be able to work in their stations. So the way they do it in aerospace is there's these things called mechanic hours, where instead of you getting an hourly wage, instead you get a mechanic hour, which is like if it takes 4 hours to change the oil in your car or something, then they pay you 4 hours wage. And that's a set amount. So no matter when you change the oil, they pay you for 4 hours. So if you're a fast worker and it takes you 3 hours to change the oil, then you still get paid for 4 hours. But if you're a slow worker and it takes you 5 hours to change the oil, then you're not gaining as much because you're still only getting paid for 4 hours. So instead of like measuring the time that someone puts into it, they measure like the effort when they choose to pay you. And companies have used assembly line structures since the start of the Industrial Revolution. This is because this is one of the most efficient ways to construct aircraft, cars, anything, since people do repetitive tasks and they become like experts in their task. Okay, this is a picture of the final assembly at Lockheed Martin, and like as you can see, they just add one part at a time, and they keep moving it down the line, until they have a finished product ready to be tested, painted, and sold. And these are the several locations at Lockheed Martin where they put the planes together, and it includes their subcontractors who will build certain parts that Lockheed Martin doesn't have the funds available to make that by themselves. Okay, and then the third and final phase of the design process is flight test. So in flight test, the engineers, they prove the concept to make sure everything functions okay. So what that means is, like, they'll say, okay, we need to make sure that this helicopter can fly from point A to point B at 10,000 feet at 70 miles an hour. So they'll fly up to 10,000 feet and they'll push it to 70 miles an hour, and they'll say, okay, that the structure of the plane's holding up by, like, using various instruments and measurements to make sure that the aircraft is safe, not only safe, but it functions well in the way that they want it to, so that when they sell it to the customer, they get a good product. And this is a little video of a flight test. Play that for me.
On June 28th, NASA's low-density supersonic accelerator project conducted the first shakeout flight on the new way of testing technologies that will one day be used to land heavier, more massive payloads on the surface of Mars. We used a large 34 million cubic foot scientific balloon that hoisted a 7,000-pound test vehicle to an altitude of 120,000 feet. The test vehicle was then released from the balloon and spun up for stability. And a large solid rocket motor accelerated to 4 times the speed of sound and an altitude of 180,000 feet, a condition very similar to conditions we see on Mars. Once we reached the correct speed and altitude, we de-spun the vehicle. And then we got a chance to test our new supersonic inflatable accelerator. Camera lens covers deployed, we see that it inflated very uniformly without disturbing the vehicle too much. And now we're seeing previously unreleased high-definition, high-resolution, high-speed video taken during the test. We used the supersonic inflatable accelerator to slow us to something closer to 2.5 times the speed of sound. We used a balloon to help deploy the new supersonic parachute. The balloon is shot out the back of the vehicle at over 200 feet per second, and then we cut the balloon free and it begins to pull the parachute off the back of the vehicle. As the parachute begins to inflate, we see one of the surprising aspects of this test, which is the early onset of tears in the parachute. We see where those tears began, how they propagated, and otherwise how the parachute behaved as it began trying to inflate behind this very blunt object, moving 2.5 times the speed of sound, punching a hole in the atmosphere, and creating an extremely turbulent, chaotic environment that the parachute was exist in. We now have a data set that we will use to prepare 2 more tests beginning in June of 2015.
Okay, so as you can see in the video, they had, like, very specific conditions that they have to follow, because they're trying to test deploying parachutes, like, more effectively for when they actually go to Mars or send people or more drones over to Mars. But in that test, it actually failed, so that they're going to have to take their parachute design and take it back to square one, back to the drawing board, so that they can more effectively create a better design and have one that doesn't tear when it opens. And also, when they're actually testing it, there are many more people than just a narrator telling you, like, what's going on. Like, they have an entire command center saying, like, okay, this is what's happening with wind. One person's on wind, one person's on temperature, one person's on altitude, and, like, they all work together, they all collaborate to, like, produce a successful test so that they can, like, find out what they're trying to find out. Can you click the next slide? Thank you. Alright, so moving on from my interviews to the research assessments. Okay, so 3 of the most interesting things that I researched this year were the EM drive, the blended wing, and drones. So the EM drive is an electromagnetic drive that can that operates in 0 gravity or vacuum without propellant. which is very interesting because no engine in the history of mankind has ever operated without propellant. So in cars you have gasoline, in airplanes you have jet fuel, in like hydroelectric dams you have water. So this is very interesting because something that's bad in space travel now is that there's like you can't take a lot of fuel up into space because you have to the more fuel you have, the more power it takes to actually get to space, the more costly it is. So this is interesting because since it has no propellant, you don't need the extra mass of taking things up into space, so that you can travel further and more effectively. The second thing I researched is the blended wing. This is a design that on a normal airplane you'd have a barrel and two wings. That's like your 747 from Boeing, the things that you fly around when you're traveling to vacation. But this one, it's just a wing, and the barrel is kind of blended into the wing so that it's more fuel efficient. The third thing I researched is drones, which are very useful tools that can assist in camera operations as well as other operations. So for example, like the firefighters in Australia use these UAV things to help plan their rescue logistics. So further in depth on the EM drive, it's not very effective right now because it's just in preliminary construction. So I think the actual numbers of energy that it produces 50 microjoules, which is much less than like these computers could even run on. But any step towards no propellant is good, and NASA has bought into this, and Boeing, and they're trying to make this more effective for space travel in the future. And then more in depth on the X-48, not only Boeing was the original designer of this aircraft, but then NASA helped them with tests, and that actually isn't a full-size model, that's actually a smaller model, and people will do this to make sure their design works before they make a full-size model and spend $6 billion building just one plane that might fail. And then drones, that's a picture of a UAV in the US military over in Afghanistan, but what I actually researched was the Australian firefighters who use UAV technology to assist them. The thing is, like, they have cameras and sensors that can detect plumage and other like details that's very beneficial to firefighters, and they use these outdoors so that because drones are hard to fly indoors. So I said, hey, I can make something that can fly indoors to help firefighters, and that's what inspired the thing I'm studying for my original work, which is the firefighting drone. And so what I plan to do for my original work, based on like all the research I've done this year, this is like the summary of it. So what it does is it's going to help firefighters locate people still trapped inside house fires and office fires, because in a fire situation, a life-threatening situation, like, every single second counts. And so you're putting much less people at risk. It's just technology, which is expendable, but people aren't. So these drones will go in, they'll locate the people inside and deliver a safe path to the firefighters who can then take those people out. And yeah, that's my research presentation. We're excited.